Hello everyone, it's a pleasure meeting you all in my mathematics class. Today let me introduce certain new concepts in modern algebra. See, let G star be a group and H and K be its subgroups. Then we define what is called the internal direct product of the subgroups of G as G is equal to HK. G is equal to H. That is, the group G is equal to H and K, where H and K are nothing but the subgroups of the group G in such a way that is, it is defined as G is equal to HK, G is equal to HK, which is a set consists of all the elements of the form X is equal to HK. The elements, any element if you take in HK, it will be of the form H into K, where H belongs to H and K belongs to K. And that this HK is equal to KH. HK is equal to KH. If we take HK. And that the representation of an element in HK is unique. Unique in the sense that there cannot be more than one representation for an element in HK. That is, it is an element in G, and the G element can be expressed as HK, and it has got a unique representation in the sense that if you have two representations as X is equal to HK and also X is equal to H dash K dash, then it will mean that H is equal to H dash and K is equal to K dash. That is, there cannot be more than one representation, and the representation is said to be unique. So this is the idea behind that. Having this, that is, you can put like this. So it is like this. This is your G, and we have got H and K like this, and you see that this G can be represented is equal to HK, and HK has got this. This is called the your internal direct product of the subgroups of G. Now, having understood what is the meaning of the internal direct product of this, so if you have it as H1, H2, H3, HK like that, you can have it as H1, H1, H2, H3, H4 like that, and HI will be belonging to capital HI. That is the meaning of that, and the representation of any element is unique, and we are going to see some of the two theorems in this particular theory. So you see that here the propositions. The first proposition is, if G is equal to HK, where H and K are the subgroups of G, then H intersection K is equal to E. That means the only common element between H and K can be only the identity element. That is, if G is equal to HK, then H intersection K is equal to E only, that is the common element. E can only be the common element between H and K. This is our first proposition. How this is proved? We have to prove this. And the second proposition is nothing but this G is isomorphic to H cross K. That is the inner product of H and K. So this is what we are going to do. Now, so let us take an element. How to prove this? Take an element in G. Now, X belongs to G, that means X belongs to HK. That is X belongs to HK. And this X belongs to HK and H belongs to, and H is an element of K and K is an element of H. And this, I am taking this X as the common element. It is the common element between H and K. Now, what I am going to establish is that this X can nothing but the identity element E, which is common for H and K. That is what I am going to prove. That means I am going to prove that the X can be nothing more than that, the identity element. This is what I am going to prove. See, H belongs to H and K belongs to K. When this is H minus 1 belongs to H because H is a subgroup. If an element H is there, its inverse must be present there. Likewise, K inverse must be present there. And this X belongs to, see here I have written here, X belongs to H intersection K. So X minus 1 must also belong to, because if H intersection K is a subgroup. If H is a subgroup, K is a subgroup, H intersection K is a subgroup. And therefore, if X is an element of H intersection K, X minus 1 will also be an element of H intersection K. So that is what I have understood. See, this is what I have written. Now you write this X is equal to HK, and this HK can be written as H identity element E and K, because identity HE is nothing but H or EK is nothing but K. So I can write it in this way, where this E is nothing but what? The identity element. Okay. Now, in this X, I can write this as H in the place of E. See, in the place of E, I am writing X minus 1, because X minus 1 is equal to E, because it is the element. That is, any element with its operation with its identity inverse is E. Therefore, X minus 1 is equal to E. So you are getting X minus 1 K. Now I split this. See, Hx, this is X minus 1 K. Now you can find that this X is an element, H is an element of H. See, H is an element of, see here I have taken, H is an element of X. X is also an element of H. X is an element of H. X is an element of H. H is also an element of H. Therefore, Hx must be an element of H. So, this Hx is an element, and likewise X minus 1 is an element of K, and K is an element of K. Therefore, X minus 1 of K, say I have written here, X minus 1 of K belongs to K, and this Hx minus this. Therefore, here again you see that any element in G can be represented as HK, where H belongs to H and K belongs to K. So you see that this is an element of H and this is an element of K. Therefore, X is equal to HK. So this X is equal to HK can be given in this form, where H is Hx and K is X minus 1K. We can represent it. We can very well represent it by the logic I have explained here. Okay. Now, H is equal to Hx. Now we have got, what is it we have proved? H is equal to Hx. So H is equal to Hx means, now left multiplication by H minus 1 gives you H minus 1, H is equal to H minus 1 of X. But H minus 1 of H is nothing but our E. Therefore, Xe is equal to E. So we have got this. So what is the common element here? So what is it I have proved here? X is nothing but what? Our E. And even if you take it in this way, K is equal to X minus 1 of K, this will also give you E. That means what? Your X minus 1 E or both, that means both X and X minus 1 are nothing but your E. Therefore, you see that this E is the only common element between H and K. That is what I observe for. X is equal to E. This implies that H intersection K, the only common element between the subgroups H and K is nothing but E. So this is our first proposition and it is proved. Let us come to the second one. We have to prove that this is G is isomorphic to HK. See, isomorphic to HK. So this is what I should prove, that if you want to prove, that is, I am going to define a mapping. See, Xi is a mapping. Xi is a mapping from G to H over K. See, from G to Xi is a mapping. It maps the elements in such a way that if you take any element with G here, it will be mapped onto HK. That is the ordered pair. That is, Xi of G is nothing but your HK, because any element can be represented Any element G, if you take in G, it is equal to HK. So it is equal to HK. Here in the place of G, I have put here in the place of X I have got. So I am taking it as G. So G is equal to HK. This is nothing but my HK. So this is an element in G and these are all elements in HK. Can you understand? So the mapping is defined as xi of G is equal to HK ordered by. That is xi of G can be represented as HK, that is equal to HK. So this is a mapping. What is that we have to prove is, prove that this xi is an isomorphism. That is, xi is defining an isomorphism between G and HK. This is what we have to prove. If you want to prove that a function is isomorphic, you have to establish that the function is 1-1. That is, it is injective and surjective. Injective means 1-to-1. Onto means surjective. So if you can prove that it is 1-1 and onto, then it becomes a bijective mapping. When it becomes a bijective mapping, it is called, then we say that an isomorphism is established between G and HK. So this is what I am going to do here. Now, so let us prove that it is first, see, xi is 1-1. Let us prove that it is xi is 1-1. After then I will prove that xi is onto. When it is 1-1 and onto, and apart from that you have to prove that xi is a homomorphism. Xi is a homo. So if I can prove all the three, then you see that this xi will become an isomorphism. That is, the xi, the function defined between G and HK, will become an isomorphism. This is what I am going to do. Now, see, what is the meaning of this 1-to-1? 1-to-1 means, what is the meaning of 1-to-1 mapping? If you, in this particular case, xi is a mapping from G to HK. If I say that xi is a 1-to-1 mapping or an injective mapping, then distinct elements are mapped onto distinct elements. That is, the images are distinct, pre-images are distinct. So if that is established, then we can say that xi is a 1-to-1 mapping. Now, for that, how to proceed? Let us suppose that here you take two elements here, you take two elements here. Let the two elements be equal. Let the two elements be equal. If they are equal there, the pre-images must be equal. If I can prove that, then xi becomes a 1-to-1 mapping. Now, so let us suppose that here, so xi is a mapping. You take an element G1 here, it goes to xi of G1. You take an element G2, it goes to the other set as xi of G2. Let us assume that xi of G1 is equal to xi of G2. So, I have taken the let xi of G1 be equal to xi of G2. Then what is it I have to prove here? Prove that G1 is equal to G2. These are all images. These two are images. The images are equal. Let us prove that the pre-images are also equal in the sense that prove that G1 is equal to G2. Now, xi of G1 is equal to xi of G2. It means that the representation of G1 is what? We know that G1 is given by, see, let us suppose that G1 is equal to H1K1, G2 is equal to. So, xi of, what does it mean? Xi of H1K1 is equal to xi of H2K2. So, let us suppose that this is what we have. Now, so we have to prove that what? H1K1 is equal to H. So, this one, xi of, see, let us suppose that xi of G1 is equal to xi of G2. So, this will mean that xi of H1 is equal to xi of H2. But xi of H1K1 is nothing but what? Xi of H1K1 is nothing but what? See, xi of H1K1. Xi of H1K1 is equal to H1K1. It goes to xi. See, I have written here. See, it is here I have written. See, xi of HK is equal to H. Okay. So this is nothing but H1K1 is equal to H2K2. But H1K1 can be equal to H2K2 if we only when the corresponding what the that is only when H1 is equal to K1, H1 is equal to H2, and the corresponding respective elements are equal in the sense that H1K1 is equal to H2K2. This will mean that H1 is equal to H2. See, this will mean that H1 is equal to H2 and H2 K1 is equal to K2. So only this means that H1. Therefore, H1 is equal to K1 and H2 into K2 means you will find that this is H1. See, because H1 here you can find that, see here H1 K1 is equal to H2 K2, therefore G1 is equal to G2. H1 K1 is equal to H2 K2 because H1 is equal to H2 and K1 is equal to K2. Both the elements are equal, therefore G1 is equal to G2 and therefore Xi is an 1 to 1. This is 1 to 1. Xi is 1 to 1. So I am able to prove that Xi is 1 to 1. So the method of proving is assume that the images are equal, prove that the pre-images are equal. If that is established, the function becomes a 1 to 1 mapping. So I have proved that it is a 1 to 1 mapping. Let me go to onto mapping. Onto mapping means what? For every image, you are able to, there is a pre-image. That means what? For every element here, you have got the what? The pre-images are present. Okay. So let us establish that. So you take an element HK. How will the elements look like here? The elements here are HK like this, and the corresponding element will be HK. The element here will be HK. When it goes over there, it is H, comma. It is an ordered parallel. So it is HK. So let us prove that Xi is onto. So for every ordered HK, there is one HK. That is because they are distinct elements are taken to distinct elements. Okay, and we say that HK there is only a unique representation for HK. And you see that this Xi of H, if you take an HK ordered pair, there will be a corresponding element G, which is nothing but HK. Okay, so that is what I have written here. For every HK in H cross K, or that is the product H cross K, there exists a G. What is a G? G is nothing but your HK. H into K. So there exists a G H into K such that Xi of G is equal to HK ordered pair, and therefore Xi is a onto mapping. So we are able to prove that Xi is an onto mapping, and I prove that Xi is a one-to-one mapping. Therefore it is a bijective. Xi is bijective. See, Xi is bijective from G to HK. Xi is bijective from Z. Now let me prove that it is a homomorphism. How should homomorphism means what should I prove? Xi of G1 G2 must be equal to Xi of G1 Xi of G2. If I can establish this, then you see that it becomes a homomorphism. Now what is Xi of G1 G2? G1 is H1 K1 and G2 is H2 K2. So the Xi of G1 G2 will be equal to Xi of H1 K1 H2 K2. But this is nothing but what? Xi of, because you see that here H1 K1, you can write it as this can be written as K1 H1 H2 K1. So you can rewrite this as Xi of H1 H2 and K1 K2. H1 here. But Xi of H1 H2 K1 K2 is nothing but what? H1 H2 K1 K2. See, H1, because that is a mapping. That is how we define a mapping. Xi of, how do you define a mapping here? It is Xi of, if you write it as HK, it is equal to H, comma K. This is how you write. Therefore, this is nothing but what? H1, H2, and this is in a bracket. I will put it in a bracket like this. I will put it like this. Now, this multiplication or this form of writing is done only in the way, only when it is H1, H2, 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 H1, K1, H2, K2. When you go for the product of this is H1, K1 here into K1, K2. So this is nothing but the product of these two is H1, H2, K1, K2. Therefore, H1, H2, K1, K2 is nothing but H1, K1 bracket H2, K2. This is H2, K2. But what is this H1, K1? H1, K1 is nothing but xi of G1 and H2, K2 is nothing but your xi of G2. So what is that I have proved here? Xi of G1, G2 is equal to xi of G1 into xi of G2, and therefore this is, see, xi from G to HK is, see, this is an homomorphism. Xi is so xi is a homomorphism. So what is it? We have proved that xi is a homomorphism. Xi is onto, xi is 1 to 1, and because taking all this into account, we can prove that, we have proved that it is xi is a bijective mapping. That is, it's a bijective mapping from G to H over K, H into K, and therefore xi is a isomorphism from G to HK. Do you able to understand? So this is the theorem, and I hope that you should have understood well. And if you have any doubts, you write to my mail address. I'll clarify. I'll continue with more doing problems in group theory and also in ring theory. Thank you.